How many of you have built or used dashboards and just got stuck with the spinning wheel of death? Anyone? Okay, a couple people. And if any of you built those, how many of you have been told or have scaled up your infrastructure, if you're using Snowflake, scaled up your warehouse size to try to make that faster? Anyone? All right, at least one person. I certainly have myself, and that's why I wanted to focus on this topic today. So the name of this talk is Speed Wins, the basics of how to push more queries through each CPU core without touching your infrastructure. I'm David Margulies. I've been a data engineer at Tinybird for just over 2 years now. I'm mostly focused on pre-sales work, but I also work with a lot of our existing customers, and I often find that that's the most interesting and rewarding work. So during this talk, we're going to walk through a use case that's inspired by one of our real customers, a real production use case that they have, where we were able to help them reduce their query time by over 99%, and also reduce their process data by 99.99%, just by applying some very basic improvements. But first, why focus on these two metrics? Why focus on query time and process data? So at Tinybird, our customers build real-time, user-facing analytics projects. And for these kinds of projects and use cases, the spinning wheel of death is just completely unacceptable. For user-facing applications, you don't want your customers just sitting there waiting, watching something load. So low latency, sub-second latency, to be more specific, is absolutely essential here. This allows our customers to build high-performance API endpoints over their data and expose that data into their applications, which enables them to have real-time analytics for their end users. But our goal is not just to build real-time analytics projects, but to build affordable real-time projects. With a lot of money, you can really do anything. You can add more CPU cores. You could add more replicas to run your queries in parallel. But really, that's not what we want to achieve here. What we're aiming for is to reduce the amount of processed data, or data processed by each query, which means that the same CPU core can process more queries, and also that you can process fewer queries, or fewer cores for the same amount of queries. And basically what this means is that you can reduce the cost associated to your real-time project. So that's why we focus on these two metrics, query latency and process data. So to explain this better, let's get into the use case. So this is, I'm going to walk through an e-commerce example where a retailer is selling different products all over the world, and their customers can purchase their products through a website or through a mobile application. And the goal of this use case is to track a sales campaign and see how it's performing in real time, so that we can make decisions as fast and as cheaply as possible. And we like to say at Tinybird that faster decisions lead to faster delivery and faster feedback loops, and speed really is the ultimate feature. So let's take a look at the data being used in this use case. So first of all, we have a table with all the events that we're capturing from the e-commerce store. This table has just over 1 billion rows, and it's about 12 or 13 gigs compressed, which is about 30 gigs uncompressed. And we also have a product dimensional table, which just simply maps the product ID to the type, whether it's arts, clothes, gadgets, and so on. And for this, I created a really simple dashboard on top of this data where we can visualize the quantity of events of items that were sold just over the last 3 hours. And you can filter on the product type, on the event type, and as we go through this talk and apply some optimizations, also be filtering on that pipe iteration to show how each change is improving the performance. You can also see there's some metadata. You can see the response time of these queries, how many rows are being read on each query, and how many bytes are being read. So now that we have an idea of what that final output is going to look like, how can we define the query process to get to that final result? So like I said, we have the original data, which has just over 1 billion rows and is about 12 gigs compressed. And that table is sorted and indexed by the customer ID. Very common thing that we see, especially for multi-tenant applications. The next thing we can do is join with that product table so that we can map the product ID to the product type. Then we can calculate the quantity of items by minute, by event, by device and product type. And last, we can filter the data that we need. So in the final output, that final dashboard, we can just have that chart on the last 3 hours. So from the original data to the output, this is what's called our transformation process. For those that are interested, this is the full query that we're going to run. And you can see in the middle there is where we do the join, then the group by for the calculation, and then finally filtering. Pretty straightforward. So this is the first iteration of the query. And there's the spinning wheel of death. So every time the filter is changed, it takes a couple seconds for that dashboard to load. This is not horrible. I'm sure we've all seen worse. But for real-time user-facing applications, this is just not going to cut it. Taking 3 to 4 seconds is just not good enough. You don't want your end user sitting there waiting for this to load with every different interaction that they have with your dashboard. And as the amount of data we have scales and the number of concurrent users grows, this is only going to get worse. So here are the stats from that dashboard, and this is kind of the worst case scenario. Queries were taking anywhere from 3.5 to about 4.5 seconds. We were scanning the entire table, reading all 1.1 billion rows, and every query was processing almost 30 gigs. So again, for a real-time user-facing analytics application, this is just not going to work. So let's improve it. At Tinybird, when our customers face these kinds of issues, really slow queries that process a ton of data, we always recommend working backwards. So once you have your desired output, then you can start working backwards through that transformation process and see how you can improve things. And we're going to focus on 2 main things. The first is we're going to check that we're following what we call the 5 rules. And the second is checking the schemas and make sure that they're optimized for this use case. So let's start with the 5 rules of fast queries. Rule number 1, the fastest data is the one you don't write. This is a fairly obvious one, pretty self-evident, but if you don't need the data for your use case, don't save it. Saving extra data is only going to impact your latency, your memory, and it's going to cost more. So if you don't need it, don't write it. Rule number 2. The second fastest data is the one you don't read. And this basically means filter your data as early as possible in your transformation process. Just as a quick example, this query here is filtering on a field that is not defined in the index. And you can see that it's reading the whole table. One column is close to 15 gigs. It's scanning all 1.1 billion rows. And it's taking about 1.5 seconds. But we can improve this by simply adding that field to the index. So this query is filtering where device is the field in the index. And you can see the result is exactly the same, but the amount of data processed is close to 400 kilobytes, and only about 33,000 rows are scanned. So the result is the same, but the amount of processed data and the latency is just orders of magnitude less. Rule number 3, sequential reads are 100 times faster. So it's not only important to filter on indexed fields, but to define your indexes correctly based on the queries that you're going to run. So here's an example where, just like in the previous one, we're filtering on device and we're also filtering on timestamp in this query. And neither of those fields are in the index. So we're scanning even more data now, almost 24 gigs, and of course, the 1.1 billion rows. And this query is taking close to 5 seconds to run. But if both fields are in the index, then it's only going to read about 500 kilobytes and 40,000 rows, which takes, 15 milliseconds. So again, same exact result, but some basic improvements, and we can see a huge difference. Rule number 4, the less data you process after reads, the better. So after applying rules 2 and 3, you should only select the data, the columns that you need for your use case. So in this example, the fields we're filtering on are in the index, so that looks good. But you can see that we're doing a select star in the query. And you can see in the results there that this is returning 6 columns, 1.87 megabytes, and taking about 23 milliseconds, so not bad. But if we only select the 4 columns that we actually need in this query, you can see that it only scans about 1.5 megabytes and takes 12 milliseconds. Not quite as impactful as the previous 2 examples, but every bit matters when you're working on a real-time project. And lastly, rule number 5, complex operations later in the processing pipeline. Always filter first. And once you have fewer rows, then you can do more complex operations like aggregations, joins, and so on. So for example, in this first part of the query, the part on the left is doing the group by first, and then the one on the right is filtering. And you can see just doing the group by is incredibly expensive, scanning about 34 gigs, all 1.1 billion rows, and taking close to 5 seconds. And then filtering, again, is scanning another 20 gigs and takes 3 seconds. So a very expensive query. But if we simply just flip that and filter first, the filtering takes about 4 or 5 milliseconds, which is pretty much nothing. And then the group by is still pretty expensive, but we've cut the amount of data we've processed in half, essentially, as well as the latency. So again, every bit counts here. So let's go back to our use case. This is the transformation process that we started with, where first we're joining, then aggregating, then filtering. But based on those 5 rules, we can optimize this a bit. So instead, we should filter first, then join, then do the group by. And here's the query. Now you can see in the middle there, we're filtering, then joining, then doing the aggregation. And back to our dashboard, let's see how we did. So make a change, and still spinning, so not much better. It's still taking 3 to 4 seconds, and it's still scanning the whole table. So slight improvement on the latency, but not much else. And again, it's important to note here that we really just changed the order of operations. We're still using the same original table that was sorted and indexed on that customer ID. So again, looking at those stats, we slightly increased the query time, but nothing else. We have to keep going. The next thing we want to take a look at is the schemas. So this is the original table that we started with. And there you can see at the bottom, the engine sorting key, which is the index, is defined as the customer ID, which, like I said earlier, makes sense for a lot of use cases, but this doesn't make much sense for this specific use case because we're filtering on the event type and the timestamp. So instead, we can change the schema so that the index are those 2 fields, the event and timestamp. And this basically follows rules 2 and 3 from before, which is filtering on the indexes and having the indexes in the right sequential order. The event type is much lower cardinality, so it makes sense to have that as the first field. And here in the transformation process, you can see we just changed the schema of the original data. And now to the dashboard. Now we see a massive improvement. The queries are taking around 30 to 40 milliseconds. Instead of reading a billion rows, we're reading about 1 million. And rather than scanning 30 gigabytes, we're scanning about 30 to 40 megabytes. So really, really huge improvements here, and the dashboard is now super snappy. And then just comparing those stats, again, we see the huge improvement here. It's a pretty obvious thing, setting the right indexes, but it always amazes me, just how using the right indexes for your use case can help. This is probably acceptable for a real-time use case. The dashboard was really fast. Our users are getting millisecond response times. But 37 megabytes is still kind of a lot to scan for what's a pretty simple query. And at Tinybird, we like to go a little bit further than this. And we have an ace up our sleeve, which are materialized views. A materialized view is a combination of a query, which transforms your data, and a table into which the result is written. And materialized views are nothing new. Most databases have them. But what's unique about materialized views in Tinybird is that they are incremental. You don't have to schedule them to run. So that the materialized view is triggered on ingestion. Every time new data arrives to your original table, the transformation is triggered, and the result of that is written to the target table, the destination. And really what this lets you do is pre-calculate your results and shift the processing from query time back to ingestion time. And so, looking at the transformation process, we can implement a materialized view to perform the join and the aggregation at ingestion time, so that at query time, all that we need to do is filter the data. And after applying this change, here's the final dashboard. Queries are running in around 9 to 10 milliseconds, and this dashboard is about as real time as you can get. And here are the final stats. So we brought the query time down from over 4 seconds to about 9, 10 milliseconds. The rows read from 1.1 billion to about 73,000. And the process data from almost 30 gigs to about 3 megabytes. So really massive improvements. And all of these are incredibly simple changes. And it's always mind-blowing for me that just with these changes that you can have this kind of improvement. And again, here's our final real-time dashboard. And this kind of performance is really what's going to give your end users a great experience in a user-facing application. So, some conclusions. First of all, hardware is expensive, but logic is free. If you have slow queries or queries that are processing a ton of data, before you go and scale your infrastructure vertically or horizontally, first take a look at your logic. These are incredibly low effort but very high reward changes that can massively improve your project. And I probably didn't tell you anything that you don't already know. Indexes, filtering early. This is not magic. These are data engineering fundamentals. But I'd still say that 90 to 95, maybe even 99% of our customers at some point hit a problem where they have a slow query and maybe it's timing out, and they say, what's wrong? We say, indexes. You're not filtering on the index fields, or your indexes are not properly defined. And like I've said a few times, when you're working in real time, every millisecond counts. So, a couple of conclusions. Number one, you can boost your project by increasing the number of queries you can perform using the same infrastructure. And this means that you can reuse your infrastructure for more queries for other use cases, or you could even decrease it and save some money. Number two, you can achieve a highly performant dashboard, which allows you to have real-time analytics. And this is especially important for user-facing applications. And last, and probably most importantly, this will allow you to reduce your bill, but still have real-time analytics. Right? It's great to have a nice user experience, but doing it in a cheap way is absolutely the best. And to close, I'll just share this real example from a customer where after implementing these changes, they share this chart with us. This is a chart that we provide in Tinybird to show the performance of your queries. Again, nothing complicated. They implemented those 5 rules and created a materialized view themselves. And you can see that at the top, the number of requests or the number of queries stayed pretty flat. Maybe it even increased a bit at the end there. But the average data processed and the average query latency just absolutely plummeted after this. They were able to decrease their process data and their query latency by over 99%. And this is just crazy to see every time for me. And that's it. Pretty quick talk. Again, I probably didn't tell you anything you don't already know, but thank you all for coming and for paying attention. Thank you all again.